This is Jason McIntosh with McIntosh Applied Engineering. In a previous video, I introduced the porous material model used in the Ares modeler. In this video, I'm going to show you how to use the SIMA impedance device to determine the parameters of porous material. The technique I'm going to use is shown on this slide. I'm going to take a sealed volume, fill it with the porous material, and use the SIMA device to measure the input impedance into the porous material. We're going to get an impedance curve that looks something like this, where we have an impedance minima at a quarter wavelength, a maximum at a half wavelength, and then this would repeat itself if we made the volume long enough. The three parameters we're after are the pore diameter, the porosity, and the tortuosity. These were all discussed in a previous video, so I won't go into them here. But we'll build a model of this volume filled with porous material, show how the predicted impedance compares to the measured impedance, and adjust the porous material parameters until we get a good fit between them. I'm going to look at 4 different materials. The first one is a bonded acoustic cotton. This is basically recycled cotton made into a 1-inch thick mat with a density of 3 pounds per cubic foot. This material is fairly nice to work with as it is made of cotton, which doesn't bother your skin if you touch it. This is regularly sold for sound absorbing material for sound treatments from this website here, ASISstorefront.com. It goes under the trade name of Echo Eliminator, and it's fairly effective, but a little pricey. The next material I'm going to look at is an Owens Corning rigid fiberboard. This material is also 3 pounds per cubic foot, but being made from fiberglass, it's not very pleasant to work with because if the fibers get on your skin, it can become very itchy. Ideally, you should have gloves and a protective breathing mask. I acquired this material from ATS Acoustics. The other 2 materials I'm going to look at are some copper-coated steel shot commonly used in BB guns. The shot I'm using has a diameter of 4.3 millimeters. Now this is not a very common sound absorbing material, but I think it'll be instructive to look at the porous material parameters for it. The last material I'm going to look at is some polyester batting. This is typical stuff that you'd get from a craft store, typically used in a quilt or pillow. I'm only going to use a small amount of this so that we can see what happens when we underfill a volume. The test volume I'm going to use turns out to be the 50 millimeter long calibration volume that comes with the SIMA device, the MAE 130. This has a length of 50 millimeters or approximately 2 inches, and it has a diameter of 1 inch. I'm going to want to create samples 1 inches in diameter. To do that, I have an upholstery punch that I've put into a drill press. Here you can see the punch being lowered against the cotton material. Now I don't turn the drill press on, otherwise it would just grab the material and kind of whip it around. But by just pressing down very firmly with the drill press, the punch will push its way through the material and you'll get some nice samples from it. May can supply these punches, or you can get them from an upholstery store. So now I'm going to take you over and show you how the measurements are done. This is the MAE 130 that we're going to use. This is its calibration volume. So we're going to fill that with the porous material. This is the bonded cotton material with some samples cut out using this punch. They came out very nicely, and I'm going to take these samples and lightly put them into the calibration holder, and we're going to be connecting the MAE 130 to that. This is the fiberglass material that's used, the Owens Corning 3 pounds per cubic foot material. The punch goes through this pretty readily, but you're still going to want to use the drill press to make sure you get a nice square sample from it. We'll be putting these in the sample holder as well. The other material is the BB shot. This is just steel balls coated with copper to prevent oxidation. And then finally, the polyester material. I'm actually going to use this full amount here, and then I'm going to cut it in half and only use half of it. So we'll see what lowering the density of the polyester does. So to measure this, I'm going to take the MAE 130, place it up to the sample holder, and I want a good seal between the sample holder and the measurement device. So I'm going to take a piece of putty, roll it out, put it around the perimeter of the joint here. Squeeze it in nicely. And now we're ready to measure the impedance into the cotton sample. Okay, back on the computer, I'm going to bring Ares up and create a new surface impedance measurement module. The device has already been calibrated, so I'm going to go to the impedance measurement. I've already entered the measurement parameters into this. I'm going to start at 20 Hertz, go to 5,000 Hertz. That's a good range for the MAE 130. I've already entered the data set name, and all I have to do is hit perform measurement. Now this measurement is going to take a little while, so I'm going to edit this out of the video. Okay, the measurement's done. We can see the data appears here, and I'm going to go ahead and do the measurements into the other materials. I won't show you that to save time. Okay, the measurements are done. I can go to the plotting section now and plot all the data that was taken. I've got the cotton material, the fiberglass, the copper-coated steel shot or BBs, the polyester, and then the half-filled polyester. I cut the quantity of polyester in half and stuck it into the calibration volume. So we can look at the data here, but we're going to want to do the analysis in the modeler. So I'm going to go ahead and go to the Files tab and save all these to a file. Select Save. Each one of these is being exported one by one now. Okay, we've exported them all, and now I'm going to create a modeler module, and I'm going to create a graph element. When I create the graph element, this window pops up. I'm going to drag it into the viewing area, and I'm going to use the advanced options feature and import all of that data into the graph buffers. So I want to do cotton first, and then fiberglass, and then the BB shot, and then polyester, and the half-filled polyester. So all that data has been loaded in. To make it easier to see the curves, I'm going to set all of the line weights to a 3. I want to make sure we're plotting impedance, and I'm going to go ahead and turn the real and imaginary on. And let's go ahead and take a look at the cotton material. So here's the cotton impedance. The magnitude in dB is in the upper graph, and the real and imaginary part of the impedance is in the lower graph. At low frequencies, the impedance is dominated by the compliance of the air volume. And at high frequencies, the imaginary part's going to 0, and the impedance is being dominated by a real part. The real part comes from the viscous losses of the air trying to force its way through the pores of the material. And that will end up dominating the impedance of this material as the frequency goes up. Now I'm going to build a model for this system. To do that, I'm going to start with a circular port. I'm going to set its length to be 50 millimeters. That's the size of the calibration volume. Its diameter was 25.4. I need to excite this with a pressure source, otherwise everything's going to be 0. I'm going to go ahead and connect the graph element up to this. I'm going to go to global parameters. I want to set the frequency range to match the frequencies that we measured with the SIMA device, and I'm going to increase the number of points to 2,000 so we have plenty of them, and hit calculate. Let's go to the graph window. So now the results from that model are shown in blue. We're seeing the quarter wavelength and half wavelength resonances, which have been damped due to the porous material. And at low frequencies, we're seeing the stiffness effect again. However, the stiffness of the air-filled volume is higher than the stiffness of the porous material-filled volume. This is due to the isothermal compressibility that was discussed in the previous video. So I'm going to go back to the model and copy air-filled into buffer G. And now I'm going to want to go and turn the porous material model on. To get to the porous material model, you select global parameters, and under fluid properties, there's an option that says use porous material. Now when we turn this on, all of the acoustic elements in this circuit will use the porous material model. So if we have other ports and volumes, they're also going to be filled with this porous material. Typically in a model, you're only going to want to have one or two elements with porous material in them. And the rest of your elements will likely just be filled with air. To only apply porous material to one of your elements, you have to create a subcircuit and place the elements to receive the porous material inside the subcircuit. This again was covered in the previous video. So now that we've enabled the porous material model with the default parameters, I'm going to hit calculate again. And now let's take a look at the model. So the air field is in red. The porous material model is in blue. It's much closer to the measured results. This is largely because I've adjusted the default parameters in Ares to match these sound absorbing materials, so we're already pretty close. To tweak the parameters in a little more, I'm going to turn the air-filled curve off. So that we can see what we're doing a little better. Note that at low frequencies, the model is matching the cotton's impedance very well. At these frequencies, the air is behaving isothermally in both the model and in the measurements. At the higher frequencies, we're off a little bit. Now this is close to the quarter wavelength resonance where we'd expect a velocity maximum. When the velocity is high, that means the viscous damping is going to dominate the behavior of the material. So if we want to tweak our parameters in a little closer, we want to change a parameter that has something to do with the viscosity. The two parameters that control viscosity is the pore size and the tortuosity. I'm going to go ahead and increase the tortuosity up to 1.2, hit calculate, and see how well we're matching. So I knew ahead of time that a tortuosity of 1.2 would get us closer, and these curves are matching extremely well. So at this point, we've got a good set of parameters for the cotton material. I'm now going to go back and turn on the fiberglass material. The fiberglass material, again, has roughly the same low frequency compliance, indicating that it's also behaving isothermally. But the impedance is a little less near our quarter wavelength frequency. This indicates that the viscous effects in the fiberglass is a little less than in the cotton. So to try to get the model to match the fiberglass, I'm going to go back to our parameters again. And this time I'm going to drop the tortuosity back to a value of 1, resolve the model, and go back to our data. Our model now is going through the fiberglass pretty well. So the difference between the cotton and the fiberglass is the tortuosity. The cotton was slightly higher at 1.2 and the fiberglass was 1.0. Now all things considered, these two materials are behaving pretty similar to one another. That's probably due to the fact that they've both been optimized for sound absorption. So we'd expect their material characteristics to be fairly close, even though they're made of different materials. I'm now going to go and turn on the data that we took for the BB shot, which is going to be substantially different. The BB shot now is shown in the light blue curve. It has a much higher stiffness at low frequencies. This is due to the fact that there's much less air in the BB shot volume than with the porous material. The BBs can take up to 75% of the volume if they're packed ideally. So there's simply less air to compress at the low frequencies. Also, at the higher frequencies, you can see that we have less damping. That's because the pore size is going to be larger with the BBs than the tiny fibers in the cotton and the fiberglass. So let's go back to our parameters and try to get them to match the BB shot. So the first thing I'm going to do is try to fit the low frequency, and I'm going to do that by dropping the porosity. Now if the BBs were packed ideally, we'd have a porosity of 25% or 0.25. So I'm going to hit calculate. Now if we look at the data at low frequencies, the model is actually a higher impedance than the BB shot. So the BB shot didn't pack ideally. We have more air in there than we were expecting. So I'm going to go ahead and increase the porosity and add more air to the model. I'm going to try 0.4, hit calculate. Now with 40% air, the model is matching the BB shot data much closer. But we've got too much damping at the high frequencies. So the two things that control the damping are going to be the pore size and the tortuosity. First thing I'm going to try to do is increase the pore size. I'm going to go up to a 0.5 millimeter, see how that does. So a 0.5 millimeter caused the impedance to drop closer to what the BB shot is doing, and it raised the impedance at the half wavelength, but we've still got a ways to go. So I'm going to go ahead and increase the pore size even more. I'm going to go up to 0.9. So we're roughly capturing the magnitude of the impedance near these resonances, but we're off in terms of their location and frequency. I'm going to adjust our other viscous parameter, the tortuosity, and see what we can do. I'm going to go to 1.1, hit calculate. So the value of 1.1, our curves are now matching the BB shot pretty well. And we'll accept that as a good set of parameters for the BB shot material. So as you can tell, presently curve fitting the impedance data to the porous material parameters is a bit of a trial and error technique. You can do this on your own, or May would be happy to work with you to implement an automated system. The last materials we've got are the half-filled polyester and the polyester itself. So I'm going to turn the polyester on. The plots are getting a little busy, so I'm going to turn the other ones off. So now we've got the polyester material in green, and we've still got the BB shot model in blue. I'm going to go ahead and enter the porous material parameters that I already found for the polyester material. They were 0.32, porosity of 99% again, and tortuosity of 0.9. Hit calculate and go back to the graph. So our porous material model is matching the polyester data pretty well. I'm going to go back and turn the cotton material back on so we can compare the difference. Note that both of them are still giving us a good low frequency isothermal compressibility performance, but the polyester is very light. I didn't put very much in, and it doesn't have nearly the damping at these resonances that the cotton material had. So this is some of the trade-offs of using your own mixture of material when you pack polyester into a volume, or when you pack any of your own material into a volume, you really need to understand how it's behaving in there. I'm now going to do the same with the half-filled polyester. I'm going to turn that on, turn the cotton off, and go back. So the half-filled polyester, which has half the polyester fill of the green data that we took, is shown in red. Again, it's very similar at low frequencies with isothermal compressibility, but we're getting even less damping from the material at the resonances. The porous material parameters that fit this data the best turns out had a pore diameter of 0.6, which is pretty large. So I'm going to hit calculate, go back. We can see that our blue curve, the model, is matching the red data pretty well. The parameters from our materials are summarized in this table. Here are the materials and the pore diameters. The largest pore diameter was the BB shot. The second largest was that half-filled polyester. When we put a very little amount of polyester in there, it increased the effective distance between all of the fibers, and so the pore size went up. The smallest pore size was with our material that was engineered to have a high amount of acoustic absorption. Porosities were all very high except for the BBs, and the tortuosities were pretty close to unity, which is typical. Another parameter that I'm listing here is something called the thermal transition frequency. This is the frequency at which we move from an isothermal compressibility to an adiabatic one. Again, this was discussed in the previous video. Usually, what you want to see is a very high thermal transition frequency, and indeed, the highest transition frequencies that we have here are from the fiberglass and the cotton material. The lowest transition frequency is from the BBs. That's because it has the largest pore diameter. And the half-filled polyester was also quite low. So chances are, if you're trying to fill the back of a speaker volume, this half-filled polyester isn't a sufficient amount of material. This was a brief introduction of how to use the SIMA device to measure the properties of porous materials. Porous materials can be very useful if they're used correctly, but you really need to understand how they're affecting your design. And the SIMA device and the acoustic modeler in Ares are both meant to work together to help you achieve that understanding and a good effective design. Thank you for your time. If you have any questions, please feel free to contact us. You can reach us at support@maellc.com. We're happy to provide these tools for you, or we can parameterize materials for you if you'd like. Thank you for your time.